Okay, so I'm happy to present to you our work, which was accepted to ICML this spring on spectral normalization applied for deep reinforcement learning. This was a really cool collaboration for me, at least, with Tudor Berariu, now at Imperial, Mihaela Roșca, Claudia Klopas, and Răzvan Pașcanu from DeepMind, and my PhD supervisor, Lucian Bușoniu. I'll present some intuitions about how we started working on this, and some basic terminology, and then I'll leave the second half of the presentation to Tudor. Okay, so most of this presentation will be about trying to explain this figure. So what is this about? At some point last year, we applied a technique called spectral normalization, which I'll get to quickly, on the usual DQN algorithm, on the classic DQN algorithm. Furthermore, we didn't apply spectral normalization on the full network, but only on a couple of layers from the classic, from the off-the-shelf DQN network, and we noticed this rather large increase in performance across many of the Atari games, right? And more importantly, this performance boost was actually greater than the one you'd see from other algorithmic improvements in this literature, right? So when we started comparing this to newer algorithms such as I don't know, double DQN, dueling DQN, or even rainbow, we noticed that this simple modification to the function approximator was actually closing the gap to more advanced and much more complicated algorithms. And really, this paper was all about trying to figure out why it is the case that this happens. Right? Now, just to have some common terminology from for all the people in the meeting. We are in the classic reinforcement learning scenario, more specifically in the value-based methods framework, where we have the classic agent environment action loop, in which the agent basically receives some observation from the environment, needs to compute some action, and then it receives a reward for that said action, right? Now, in the classic DQN algorithm we've worked with in this paper, this training procedure, this is to basically minimizing this objective, where we sampled some transitions from a replay buffer. And then we try to minimize this mean squared error between some bootstrap estimate of the Q value and our current estimate, the estimate at the current state, right? And another algorithm we've used extensively in this paper basically extends this idea from DQN, in that now, instead of estimating point estimates for our Q values, we now try to estimate a distribution of returns, right? So if this would be DQN, where for each action we have some Q value, which is a scalar, a point estimate. Now we would try to estimate some distribution over possible future returns, And then the objective we are interested in reduces to basically a cross entropy between two distributions, right? The distribution at the current state, and again some target distribution, which is computed in a rather specific way for this algorithm. But basically, this is still a value-based method, right? So this is the setup. Now, it's important to say that for a while, we believe that these improvements we were seeing were due to this rather specific objective function used in categorical reinforcement learning. But as you've seen already in the previous plot, that was actually not the case. Okay. Now, before we go into discussing about spectral normalization and our results, I wanted to paint some. To paint some picture about the optimization landscape in reinforcement learning. So it turns out that especially in value-based reinforcement learning, we had a hard time characterizing what are the optimization dynamics. And we felt that this is actually quite an important point to think about when discussing these results, right? So there are a couple of strange empirical observations in the literature, which I feel are kind of important for the context in which we are, and I wanted to at least point to them here, right? So on one hand, there's this paper from Emmanuel Benjo, which shows that value-based methods, TD0 in particular, operates in what's called a low interference regime, which in supervised learning is usually associated with overfitting. However, this very same regime, which in supervised learning is associated with overfitting and having a large generalization gap, is actually good in RL, right? And we don't know exactly why it is the case. Also, there's this other work from Kumar, which we actually used in our paper at some point, which shows that again in temporal difference learning, there's a really abrupt loss in the number of features being used by the function approximator when estimating the Q values. And again, this loss of feature space is not, of feature rank, is not really understood. But we had some experiments showing that with our method, we are actually able to reverse this observation they had, right? And also, there's this again this nice work by Romov showing that it's actually really difficult to bring new optimization methods in reinforcement learning, in the sense that you can go on about taking methods which in theory should produce an improvement, but in deep reinforcement learning, it seems that it is not the case. So in this case here, for example, they propose something akin to natural gradient descent. Is basically a second-order optimization method which learns an optimum hyperparameter for an optimum learning rate for each of the parameters. But they actually show that experimentally in deep reinforcement learning, this brings no change. And I hope that I was able to create a confusing picture of the optimization landscape in reinforcement learning, because this is how I felt. This is how we also felt it is the case. And at the same time, I think it's kind of important to connect this kind of work to some of the results you'll see later in this presentation. Now, it's worthwhile to mention that in policy gradient methods, usually intuitions about optimization actually produce good algorithms, right? So if you look at stuff like trust region policy optimization and proximal policy optimization, these are basically just optimization methods carried onto policy gradient methods, and they actually show meaningful gains. Okay, now in order to talk about spectral normalization, I'll first just introduce a couple of concepts related to Lipschitz continuity. So basically, we say that a function is, in this case, a univariate function is K Lipschitz continuous if basically a small change in the input of the function produces a small change, correspondingly small change in the output, right? So equivalently, this means that the slope of this function is bounded by K, right? So another way of saying this is that if this function is K Lipschitz across its support, then for every x there's a cone, and the rest of the function lies on either side of this cone, right? Now, going forward to the more interesting case, to the multivariate case, we can look at the simple linear map, right? Such as this function here. And in this case, for some matrix A, we say that this function is Lipschitz in some norm if the norm of the matrix is also bounded by K, right? And it's interesting that you can actually look at multiple vector norms which induce various matrix norms, but for our work, we were actually only interested in the Euclidean norm, for which case the equivalent matrix norm is the largest singular value of A. And again, the intuition here is that we're basically interested in the degree to which the matrix A changes the magnitude of some vector x, right? So this is what I was kind of trying to depict here. Now, what's important to know is that this carries out nicely to neural networks, right? So we know already from the previous slide that linear layers basically can be made to be K Lipschitz if we constrain the spectral radius of the weights of the weights of the linear operator in case. Now, ReLU nonlinearities, max pooling, batch normalization are also functions which can be one Lipschitz, which are one Lipschitz actually. And also, it's a bit more convoluted, but since convolutional operators are also linear maps, they also can be made to be one Lipschitz. And since we have this nice property that the Lipschitz constant of a function is bounded by the product of its components of the Lipschitz constants of its components. What this essentially means is that we can make an entire network which is composed of these basic elements like ReLU, nonlinearities, max pooling, and convolutions and linear layers to be K Lipschitz, right? And most often in the literature, the only thing you need to do for this is to find an efficient way of computing the spectral radius of the weight, right? The largest singular value of the weights of any given layer, and then just divide the weights by that by that value, right? And again, in the case of in the linear case, we can do this with a kind of one-step power iteration, right? We can approximate the largest singular value, and we can do this at inference time, right? So every time you do an inference from through the network, you can also do one step of power iteration, compute an approximation to the spectral radius, and normalize our weights, right? And you can see that this is really not computationally expensive. However, in the case of convolutional layers, things get more complicated in the sense that these two operations here are now convolutional operations and transposed convolutions. Right, so this is an implementation detail. You can find all the juicy details in this reference here. But the point is that it's fairly easy to constrain the Lipschitz constant of a network. Now, in most of the prior work, you will see that the network is fully normalized. That means that we compute an approximation of the spectral radius of each layer, and we normalize the entire network like this, right? And this allows us to say that, look, the Lipschitz constant of this network is now bounded by the product of the spectral radii. Now, in our work, we take a different route in the sense that we decided to actually normalize only a subset of a network's layers. And generally, we noticed that it kind of works best to normalize the layers with a large number of weights. And there are also some intuitions for why it is best to kind of restrain to the hidden layers only. So, for example, in the case of value-based reinforcement learning, you can see that, for example, if you normalize the final layer, this means that you are actually putting a constraint on the Q values the network can express, and this is usually not a good idea. And we also thought about normalizing the input layers, but we kind of noticed that they are kind of sensible to this in the sense that the expressive power of the network seems to drop whenever we normalize the first layer. So maybe this has something to do with the fact that you learn some basic filters here, which really don't need to be Lipschitz smooth. Okay, now I also, just before presenting some of the results, I wanted also to provide some context regarding spectral normalization. You'll see it used in supervised learning, for example, in the literature regarding defense against adversarial examples. So the intuition here is that because adversarial examples are basically ways of producing a small change in the input in order to trick your network, your classifier, you might want to train networks which are inherently smooth, hoping that this will help you to protect against these kinds of attacks. they're also encountered in the literature of uncertainty estimation. So if you've ever tried to generate some, to get some uncertainty estimates from neural networks, you'll see that outside the support of a neural networks, the outputs are really wild, and you can use spectral normalization to actually induce this smoothness bias to your class of functions, and hopefully this way you also get some better uncertainty estimates, especially outside the support of your data. And really, for a really in-depth overview and some motivation for why it's important to think about smoothness in training deep neural networks, there's this nice paper by Michaela, which I encourage you to look into. Okay. And of course, probably the poster child of spectral normalization is this result in unsupervised learning, where spectral normalization was used to impose some theoretical constraint you have on the Wasserstein formulation for generative adversarial networks. So basically, in order to be able to optimize the function of the dual form of the Wasserstein distance, you actually need to make sure that your function is Lipschitz. And in the first iteration of that work, you are just clipping the weights in order to make sure the function is Lipschitz. But Miata et al. Figured out how to use spectral normalization in order to meet this demand. In reinforcement learning, there was really not much regarding spectral normalization. There's this paper by Yu et al. In which they're actually doing model-based reinforcement learning, and they're using spectral normalization specifically to get this kind of robust uncertainty estimates, right? And then after we published our work, there's this paper by Bjork et al., which they're doing they're taking a similar approach to ours, but in the case of deterministic policy gradient methods. And we actually have a slide about this. Now, there's another interesting thing about this literature on spectral normalization, in that some of these works are actually also about a special regime of the data, in the sense that data is often non-stationary, right? So the data comes from some non-stationary distribution, or even your target, your learning target, is not actually sampled from some kind of stationary distribution. And we kind of have some extensions to our work, which will try to look into this issue. If spectral normalization, or the results we are seeing with spectral normalization, have something to do with this non-stationary regime of the data or of the targets. Okay, now again, the main empirical result we get with spectral normalization on the almost full Atari suit, right? We tested on 54 Atari games, is that if you take C51, which is that kind of distributional algorithm I was showing you a couple of slides before, and you apply spectral normalization on the largest linear layer in the network, the one just before the output, you get this, again, this large boost in performance, which actually rivals Rainbow, right? And Rainbow Rainbow is the kind of algorithm that is really complex, in that it uses contributions from the last couple of years in reinforcement learning. It uses stuff like prioritized experience replay, dueling networks, double DQN, it actually uses this very objective in C51 also. And on top of that, also a technique for exploration called noisiness, right? So there are like 5 algorithms in Rainbow, making it a really difficult algorithm to train and to tune hyperparameters and all that jazz. Okay, so besides this kind of blunt result, we wanted to figure out if we can empirically characterize the behavior of spectral normalization. And in order to do that, we went away from Atari and we selected another benchmark, which was more computationally efficient, called Minotaur, which is a collection of 4 games, 5 games, but we only used 4 for a good reason. 4 games which basically re-implement Atari, but in a smaller state space. Okay, and the first thing we looked into was what is the relation between spectral normalization and the capacity of the network, right? So what happens if you try to increase either the width of the network or the depth of the neural network? And what we noticed, so all these are averages, normalized averages over the 4 games, right? And usually each algorithm here was also trained on like 10 seeds, right? So the reason these averages here are smooth is because there are actually lots of training runs beneath it, right? So what we noticed was that whenever we increased the capacity of the network, we usually the baseline got kind of lesser results than the optimal architecture. So we kind of noticed that in most instances, deviating from the optimal architecture would actually hurt performance. So just scaling the network does not really help in value-based RL. However, whenever we applied spectral normalization on either one layer or multiple layers, we were actually able to either preserve the bus performance or actually go higher than any baseline we encountered in our experiments. So at this point, spectral normalization seemed like a good way to regularize your model in instances where you have a large model. Oh, also, these averages are also on different learning rates usually, right? So just to make sure that we have a good signal. Okay, now we also wanted to figure out if this is something to do with the presumed smoothness of the approximators we were now getting when normalizing with spectral normalization. And to get an intuition about this, remember that we were not normalizing the full network, right? So we were only normalizing like one or 2 layers, or maybe 3 layers in an estimator. So what this means is that we cannot surely say that the network now is K Lipschitz in any sense, right? We don't know at this point what is the Lipschitz constant of the network. The problem is that like for 2-layer Rayleigh networks, computing the constant Lipschitz is actually NP hard, right? So we cannot do it analytically. So what we tried to do was to kind of look into the neighborhood of the data and and just estimated from estimated for the samples on which we trained on. So to give you an intuition about this, there's this nice figure from Michaela's paper in which she samples data from around the training data, where the training data is this are these dots, right, in blue and red. And basically they compute the Lipschitz constant with respect to this sample data on the grid. And what they show is that, for example, if you don't have any regularization, the Lipschitz constant outside your training data can get really hard, like really high, like values of 100. If you do something like gradient penalty, so this is kind of a soft version of spectral normalization, where you just have a regularization term based on the norm of the spectral norm of the weights. You get these rather smoother networks, and in the case of spectral normalization, you actually get large regions around the data, which are smooth, right? So what we did was to train many agents, like I don't know, like 10,000 agents or so, on 12 networks of different sizes. So there were like I think there were like 3 or 4 different depths and 4 different widths. And then for each of these agents, multiple seeds each, right? And for each of these agents, we measured the norm of the Jacobian of the output with respect to the input, right? So this again, this is a bound for the true Lipschitz constant of the estimator we were using, right? And what we did was to plot this norm on the x-axis and the performance on the y-axis. So the way you interpret this is that when the dots are to the left, right, you got smoother estimators, right, and when they are to the right, you get agents with a large Lipschitz constant. And what we wanted to see was if across different model sizes we could get any correlation between the Lipschitz constant of the estimator, the empirical Lipschitz constant of the network, and the performance of the agent. And unfortunately, across different games and different network sizes, we could not get a reliable estimate, a reliable correlation, right? So we could not actually say if smoothness indeed has anything to do with performance, right? So basically, the smoothness hypothesis we got kind of went out the window with this experiment. Okay, before I leave it to Tudor to present the second part of our results, I wanted to show you this other plot we did at some point, in which we trained agents on a very large hyperparameter sweep. Again, there were like 6 different architecture sizes. This is again an average over normalized scores. And what we wanted to see was if applying spectral normalization would allow us, for example, to have a different performance profile depending on the selection of learning rates and epsilon values in the ADAM optimizer, which is kind of a finicky hyperparameter in reinforcement learning. So what we got was that spectral normalization actually gave you a wider a wider band of good hyperparameters. And this is actually something we also observed in some more recent experiments on policy gradient methods also. So it seems that all in all, it's a good idea to have like one of your layers normalized in order to at least make sure that you'll maybe get more robust agents to various changes in the learning rate, for example, right? By the way, these are results with ADAM, but we have some, in the paper, we have some results with our RMS prop also. So I'll leave it to Tudor now to discuss the other results we got on this.
Thank you, Florin. Okay, so Florin left me with the boring part of the presentation. That is going to be a bit more technical, but yeah, let's see how it goes. So as Florin said, we had some hypotheses on why would spectral normalization be useful in reinforcement learning or in non-stationary setups in general. And smoothness was, of course, the first hypothesis because it's what directly such a constraint controls. But if Florin convinced you with that plot with the colored balloons, smoothness does not necessarily explain this. So what we did next was to try to look at the different quantities like activations, gradients, optimization steps, and so on, and see if we can describe somehow relations between those quantities when we apply spectral normalization, as we did, and the same quantities you get on a vanilla neural network, right? So basically the question we try to answer in the next slides is if spectral normalization has mostly an optimization effect on the training process, and that's where the boost of performance comes from. And what we're going to do next, and this is the technical part, is we're going to propose a series of approximators to spectral normalization, which should be increasingly relaxed, right? So we are relaxing the approximation to the original method incrementally, and we are incrementally approaching a method which is isolated in the optimizer, right? And by optimizer, we mean whatever function we use that takes some gradients and proposes some optimization step in the parameter space. Okay, now for those who want to leave early, I'm just going to give you the summary of what follows next. So we kind of proposed three approximations by taking these spectral values, and instead of dividing the weights at the specific layer, we try to divide the outputs, divide the gradients by the same number, or work on the dampening term in Adam. And as you can see here in this plot, which collapses several models trained on several gains, the average performance of all these approximations to spectral norm and spectral norm itself work way better than the baseline. So basically, this is like an empirical evidence to support our claim that the ways in which spectral normalization helps is through changing the optimization dynamics. Okay, so first, as I said, we try to compare the different quantities you have in a neural network, like the activations, the outputs, the loss function, the gradients, and so on. But if you think how spectral normalization is usually applied, we just we have a linear layer and we divide the weights by that number, the spectral radius, and then we do the affine transformation we are used to. Now, if we do that at a specific layer and we try to compare the activations we get when we apply spectral normalization with those in the standard case, we can actually make a direct, define a direct relationship between those, because at least for ReLU networks, what we get is a different set of activated units, right? So it's not just scaling, but the units that are being activated that are in the positive or negative regime in pre-activations are different. So we did a first approximation to spectral normalization in which we actually changed scaled the bias term as well. So we did it in such a way such that the activations we get at after applying the normalization would be just a scaled version of those we get in the standard case. All right. So in essence, if you consider that you want to do spectral normalization on a subset of layers, right? You take the spectral radii of those layers, and in this approximation, you would just get the product of all those, right? So you multiply all the spectral radii you want to consider, and you divide the outputs by that number, okay? So this was the first approximation, one that worked almost the same in, with almost the same pitfalls or the same vulnerabilities as spectral normalization, and basically showed that it's not that important where you do that, where you apply the normalization in the computational graph, but it's more about the scale, right? So the important value is the value of the spectral radius rather than where that division happens in the computational graph. Okay, so then we try to look at the gradients, right? So what we have here is a comparison between the gradients or the partial derivatives of the loss function with respect to the weights from some layer, right? Compared with those we get when we just divide the outputs, right, by that product. And we see that there are two things that change. First, the gradients are scaled with the inverse product of the spectral radii, right? And then there's a change in the Jacobian of the loss function with respect to the outputs. Now, what we did next was to kind of ignore that green term, right? Or to ignore the fact that the green term is different from the one in the standard case. And we just isolated the scaling effect, right? So what we are keeping next is just the scaling effect of spectral normalization. And we argue that at least in our case in DQN, right, which is trained not with the mean squared error, but usually with the Huber loss, right? In the Huber loss, when you have like large displacements, right, when you have large errors, the norm, what you're optimizing is actually the L1 norm, right, of that displacement, whose gradient is just the sign, right? So what I'm trying to say is that that Jacobian itself shouldn't affect the scale of the gradients too much. Okay. Now, so what we propose next is to, instead of perform spectral normalization as it is, just take the spectral radii of the layers you would normalize, multiply them, and divide the gradients by that number. Okay. So what we get is a data-dependent scheduler that scales the gradient between feeding them to the optimizer. Okay, so that would be our second relaxation, the second relaxed approximation to spectral norm, which works sometimes even better than the original. Now, to go further with our analysis, we looked at the optimizer that's used mostly today, and that's Adam, is the one we used for, at least for the experiments on Minatar, and I think on Atari with C51. I hope Flavin will correct me if that's not true. Okay, so in Adam, again, with some mild assumptions, which in practice, in our experiments, always hold, that the spectral norm doesn't change too much during training, so you won't see jumping from one layer to from one step to the other, and that might be because it doesn't the spectral radius, it's quite stable during training, it doesn't change much itself, or because we just did that one step of power iteration like everyone does, and our value was not changing, our approximation of the spectral norm wasn't changing too much. So anyway, considering that, we could work a bit the formula for the optimization step of Adam, the one that you're seeing here. Just a reminder, in Adam, you have this exponential averages of the first and second moment of the gradients. And basically, if you think that all the relevant terms in that exponential average are scaled by the product of spectral radii, you can basically divide it and isolate that scaling effect in the dampening term of Adam. So in the end, we got to this modified Adam optimizer, in which we change the dampening term by multiplying it, by scaling up with the product of the spectral radii we want to consider. If you think what's actually happening here, in all of our experiments, the spectral norm would increase during training. And how does that change the optimization step? Well, initially, this term here was introduced in Adam just for numerical stability, right? So its importance was not theoretical, but rather practical for numerical reasons. So, but if you can you switch back to the previous?
Sure.
Okay, so sorry. If you look at the denominator, right? If in that sum the second term starts to dominate numerically, right? It starts to be bigger than the square of the exponential average of squares, then what you get here is mostly an HDT with momentum, right? So what we're trying to say here is that what this scheduler does is slightly shifting to training from a pure Adam optimization step to an HDT with momentum one. Okay, now just to summarize all this technical part, we got 3 optimizers, right? In which we don't locally apply that division by the spectral radius on some parameters, but we rather take all the spectral radii, we multiply them, and we scale the gradients, the outputs of the dampening term in Adam. And all these three approximations improve over the baseline, and they are comparable with spectral norm. What's more interesting is, at least in this set of results that we had here, there are cases, there are architectures and choices of subsets of layers to normalize in which spectral norm fails for some reason, right? So we basically consider that there's a too strong regularization that happens in that case, right? That's why our best results and the results that we report are where we normalize a single layer. Right, so there are some cases in which spectral normalization fails, but if you look at these plots, especially in the bottom right part, there are cases in which operating on the gradients or on the dampening term of Adam actually performs better than still brings an improvement over the baseline. And those are the cases where, if I'm not wrong, spectral normalization fails. Right, so just to summarize it, we basically derived the optimization effect of spectral normalization, and we empirically showed here that it actually recovers the performance boost you get with spectral normalization. And we claim that probably optimization is the way to which spectral normalization boosts performance in these non-stationary setups. Yeah, so parallel to our work was this one from Cornell, where they apply spectral normalization on policy gradients methods. I think it was a soft actor critic they use here. Their approach was a bit different in the sense that they said, okay, look, we have all these modern architectures that we are using in computer vision and other domains, but deep reinforcement learning is quite behind on that front, in the sense that we're still using the same small convolutional neural network, and we have troubles in adapting more modern architectures for the deep reinforcement learning algorithms. And they show that you can do that if you apply spectral normalization. So to summarize, the claim is that spectral normalization helps you in using deeper models and more fancy architectures in deep reinforcement learning, as opposed to the classic approaches or classic regularizers. Yeah, so I guess this was it in terms of results. We are still left with some questions. We know that spectral normalization helps in these setups, but we don't really know what is the problem. So I think one interesting question that it would be good to have an answer for is what's actually the problem that spectral normalization tries to solve here? And another conclusion from our work was that the optimizers that people proposed, usually for very good reasons, studied in the supervised case, and which were kind of blindly adapted for deep reinforcement learning, might not be optimal for that case. So our intuition is that we kind of need to study this, and there are some recent papers that try to do that, try to look at this. What would be a good optimizer for reinforcement learning or for non-stationary cases, to be more general. Yeah, so I guess this was it. If you have any questions, we're happy to answer or discuss more. Thanks for your attention.
Okay, so I guess that if there aren't any questions, I guess we can kind of conclude for the evening. But again, if you have any I don't know, interesting observations or again even questions, feel free to reach any of us. And again, thank you all for attending.